Hello everyone, this is our project for mechanics of materials at the German Jordanian University under Professor Ahmed Al-Muhtadi. We chose questions RA2 and RA3. We chose them because they are simple yet they include most basic statics and mechanics ideas. We built a proportional model of question RA2 and RA3. We scaled the model so that every 10 grams equals to 1 kilogram and every 20 centimeters equals to 1 meter. As you can see here, we have 40 centimeters in length, which is equal to 2 meters, 60 centimeters in length, which is equal to 3 meters, and here we have 34.6 centimeters, so that we have the angle 30 over here.
To solve this question, we need to first get the statics part. So first we need to get the internal forces, internal reactions for the cross-section BB. And to do that, we need to first get the reaction, the force of BD, the tension force. And we need to also get the weight, which is the mass times gravity. And then we're going to get the moment at point A to get the force BD, which will leave us with the force after calculations. We're going to get to 161.6. And to get the internal forces of BB, or internal reactions, we need to get the f of x and f of y, and this will leave us with AX as 130.8 Newton and AY at 422.752 Newton. And as resulting, we have compression on the cross-section BB, which will result in a negative normal stress of negative 422.752, and with shear force of 130.8 newtons and moment of negative 138.8.
To find the internal reactions at section AA, we need to first use the equations of equilibrium, taking the moment at B to find the force caused by the two-force member, which is equal to 550. And then we take the summation of forces on the x-axis to find the force caused by the point B on the x-axis, which is equal to minus 392.4 newtons, which means it's going to my right. And taking the summation of forces on the y-axis, we find the reaction of point B on the y-axis, which is minus 196.2, which is going downwards. Now taking the internal reaction at section AA, cutting it, we find that the normal going outside is equal to 392.4 newtons, and the shear stress is minus 196.2, which means it's going upwards due to the sign convention. And the moment is 98.1 newtons meter going anti-clockwise.
Now, to get the stresses on both sections AA and BB, we should first find the area on both cross sections given the dimensions of both. The area for both is base times height. Also, we should find I for both cross sections, which is the moment of inertia, which has the formula of 1 over 12 base height cubed. And also we should find Q, which is the moment of the cross-sectional area, whether above or below the given point where the shear stress is to be determined. Now for finding Q, we should multiply Y by A. Y, which is the distance from the neutral axis to the centroid of our new chosen section. And the A is the area of the chosen section. So for A, we took the above part from our given point, since the shear stress is going down from cross section A. So we took the above part and found the area of it, and found the distance between the given point and the new section chosen, and we calculated Q for cross section A. For cross section BB, we took the right part as our new section, since the shear stress is coming from the right side. So we also found the distance between the neutral axis and the centroid of our new section and multiplied it by the area of our new section, finding the Q for both.
Okay, as a result of the numbers my colleagues have given for the geometry part and the statics part, we will calculate the normal and shear stresses for the sections AA and sections BB. First of all, I'd like to start with the section AA. As we know, there is a set of forces in point B, which are Bx and By, and also from point B to the cross section AA, this will result in a moment. Okay, for the Fx force, as it's obvious, it intersects the cross section, so it will affect the normal stress. Same goes to the moment. Since the bending is directly related to the normal stress, the moment will be included in calculating the normal stress. So, first of all, I will start with the f of x. As we have solved, the b of x section will go in the negative side, and the reaction force in the cross section AA will go to the opposite one. This will result in a tension force. The tension force will result in a positive normal stress. Same goes for the moment. Since the moment is positive, we will directly substitute the value of the moment to the equations we will solve on. We will divide the normal force or the axial force or the f of x by the area, and for the moment part, we will multiply the moment by the distance from the centroid to point E, which will be, as a result, which would be 37.5 minus 25 millimeters, which would be 12.5 millimeters, which is approximately 0.0125 in meters, all divided by the moment of inertia. For the shear stress part, we will take the f of y since it's parallel to the cross section we are given, and we will multiply it by the calculated statistical moment, and we will divide it by the moment of inertia multiplied by the width of the beam. For section BB, as my colleagues have concluded, there will be an x force and a y force in the point A. As it's obvious from here, the f of x will result in the shear stress. And why? Because it's parallel to the cross section we are given in here. And then in the contradictory, the normal force will be considered as the f of y since it intersects or is perpendicular to the cross section BB. So, as a result, for the normal stress part, we will calculate the f of y we have concluded, or the f of y reaction we have concluded, and the moment, which we also have concluded from the equations of equilibrium. The f of y for the point A is going up, and as it's obvious from our calculation, the f of y for the BB section will be going down. This will result in a compression. That's why it will, as a result, it will result in a negative shear stress for the force part. Same goes to the moment. Since the moment is negative in that section, we will also subtract them from each other, which will result in a 695.24 kPa. And then, after all, we will calculate the shear stress, which we will get from the f of x, because it's parallel to the cross section, as I have mentioned before, which will result of 31 kPa, approximately 31 kPa.
So why is it important to know the amount of stress an object experiences when a certain force is applied? Now look, materials can be classified into two categories, ductile and brittle. Ductile materials can sustain much larger amount of stresses before it bends or fractures, while brittle materials, such as in our case here, would fracture on much less amount of stresses. When building any kind of designs for beams, joists, rafts, etc., It's very important for you to calculate this amount of stresses, to calculate the amount of stresses the object can sustain before it fracture, to prevent any type of crisis from happening. Thank you for watching, and I hope you liked our video.